Okay, so I would like to say some things about new results I can see for the generic chaining. Obviously, there are, in my opinion, some minor improvements, but obviously there is a lot of work to be done, and I can encourage you to to think on them. So first, let me struggle through the introduction. It's all of this stuff was given in the morning. So for example, the most important class are Gaussian processes. And Gaussian canonical processes are obviously processes of this type. And we know that there is one good distance we can use for Gaussian. It's pretty important for what I'm going to say. And this is just Euclidean distance when you're considering Gaussian canonical processes. And why there is a special role of this Gaussian canonical process is because when we have any Gaussian process, then whenever it's separable, we have a Karhunen-Lev theorem. So each such process can be represented as a canonical in the canonical way, and that's why these canonical processes are famous. And that's why it's important to consider not only Gaussian processes, but also other classes. And obviously, our quantity of interest here is the expectation of supremum. And in a similar way, we can construct canonical processes for random signs. And once again, this is the important thing to estimate. And in the most general case, maybe general in the world of independent random variables, are canonical processes where we can simply, for simplicity, assume that all the variables are symmetric and of variance equal 1. And then what is usually assumed to get interesting things are that there is a concentration, there's a hypercontractivity. And the hypercontractivities of this type, it will be important for me when I will turn to the general partition scheme that concerns multiple distances. Then this will be important property, and the multiple distances are advertised here. So we can consider moments, and moments is a good source of distances for such general class of processes. And let me define dn as just the 2 to the power n moment of an increment for such a canonical process. Obviously, there is one important distance, which is d1 in this formulation, and this is exactly, once again, the Euclidean distance. So first important thing, which was obviously shown in the morning, is the gamma 2 numbers are, and the gamma 2 numbers are defined in this way that we consider partitioning, and each partition cannot be too large, so we can control on each step of partitioning the number of its element. And I will use many times this 2 to the power n, and that's why it's good to remember this notation. That's why I'm using here capital N of this type to denote this, because I will need these numbers, and I don't want to write this double superscript. Okay, and now with the usual notation. So if you have partition element, we can match with this partition element that contains point T, and we have the diameter of a partition element. We have our usual definition, which is the gamma 2 numbers infimum over any admissible partition, and the sum over distances and with such weights. Okay? And what is important, due to Talagrand, we know that expectation of supremum of any Gaussian process is comparable with its gamma 2 number. Okay? Another important class, when we know what to do are processes of random science. It was for a long time it was a conjecture, but finally we could prove the following characterization, that if we know what is the decomposition of a set, and the decomposition for us is any sum in L2 world when we sum two when we sum two sets T1 and T2 in the following way, and if we can decompose the set T into part when we can apply L1 norm, so it's exactly here, and the part when we can, which is sub-Gaussian, so we can use gamma to numbers. We know that such an infimum is indeed comparable with BT, but the problem with this result, I will turn to this in a second. It's more and more complicated. We are using different partition schemes, and the partition scheme for this conjecture is pretty involved. So that's why probably still it waits for some development of this idea, and I will say some words about this at the end of my talk. And now for canonical process, as Tomek Tkocz told us, we have gamma z functionals, and these gamma z functionals is a smart application of this family of distances. So if you have family of distances, and you should know that this idea works not only for canonical processes, it could be used to any process, in the sense that we can control the expectation of supremum by quantity of this type. When we use diameter, and the distance is by moments of this time. Okay, and once again, this is one more comment here. The language of admissible partitions can be replaced by admissible nets. It was also mentioned in the morning, and we have that this family of admissible nets must be nested, and what's more, we know that we need that obviously Tn. So there are not too many points in the approximation level Tn. Okay, and we can replace this functional gamma z by a functional which I can call gamma bar z, and replace the idea of partition diameter by just finding any projection on the set Tn from the point T, and we can replace this in the following way. It makes look very similar, but know that if we consider, no, it will be later. So later I will comment why it may be of interest to replace. It's easy to see that this is somehow better. So it's better because when we have a partition, we can pick one element from each partition element, and obviously you can do this in the nested way. So it's described here. If a partition is nested, so we can produce the admissible nested sequence of subsets, and now if we project exactly on this element, then and collect in the set Tn the family of all possible points of this type, then we will see, using this small requirement of hypercontractivity, that gamma bar is always dominated by gamma z. Now, what we know is that this is the simple part, and it can be proved in this way. I think it can be proved in pretty good constant. Not, I recall it was 258. No, it can be proved with constant 2 or 3, as far as I remember, but by using moments, obviously. You know that the difficult part, and I will comment on this later, is to prove the lower bound. And we know that for some families of processes, we know that this idea works. But obviously, this simple form of gamma functionals cannot deal with any canonical process, and the simplest counterexample is for Bernoulli processes, because for Bernoulli processes it's good to use just the L2 basis, and if we use L2 basis, then it will be clear that gamma x must be infinity in the formulation I've stated, but this is definitely smaller equal 1. But the problem is, if we replace this gamma x by gamma bar, still it's comparable to 1. And this is due to the fact that we can keep the same point for when approximating t, and this is an exercise. You can see that. So still, my belief is that it doesn't work for Bernoulli, because you simply have to change counterexample, but there is some differences you should be aware when using this stuff. And now I would like to say something about computer science. So I was trying to find, this is some challenge for me, how to provide an algorithm for random signs, which could be similar what was known for Gaussian case. Now what I state today will be my small simplification of the algorithm, which is due to Ding, Yuval, and Perez, and that concerns the Gaussian situation. So I go through the Gaussian situation, and on the Gaussian situation I will comment where are difficulties when I want to extend this idea to the case of, say, canonical process, and in general, obviously, we mean to do something with random signs. And the point is that we would like to have something that computes the expectation of the supremum in the time that is polynomial than the number of elements in the set T. So the whole idea is based on the partition scheme, and for the partition scheme, as Jelani Nelson stated in the morning, is pretty smart, pretty simple, pretty elegant for the Gaussian case, and it goes like that. If we have points that are well separated, so we know that the points are in some ball, and you should know that my ball is always intersected with a set T, because otherwise I would, each time I'm using this notation, I cross this with set T, and I don't want to do this. And if we know that we have a family of sets that are well separated, so they are covered by some ball of radius j negative 2, so it's a bit smaller than the level of separation, we know that we can gain something, but we can gain something only when we go to the set which is of much smaller diameter. And this is the perfect case of which works for Gaussian processes, and basically it goes through the Sudakov minoration, and you've seen in the morning how to prove it in effect. So now, why this partitioning scheme may be important? Because it always proves that we have that such functionals dominates gamma 2 numbers. One of the simplest proof I wrote a couple of years was to use the notion which was mentioned in the morning, majorizing measure. And the simplest proof goes that you fix one probability measure on the set T, and you can easily prove that if a family functional satisfies growth condition, then it must be dominated. So such a functional for a probability measure must be dominated by what we've got from the partition scheme. And that's why, if we know a little about the functional analysis, we know that the supremum over over all probability measures on the set T is comparable with the existence of the majorizing measure, and that's why we know that it's also comparable with gamma 2 numbers. But obviously, there are several proofs of the fact that having a family of functionals that satisfies the growth condition, and one of them was early in the morning, we know that it must dominate gamma 2 numbers. So the picture is that having the growth condition satisfied, we know that this functionals dominates gamma 2 numbers. Okay, but one more comment which is important for computer science. For me, it's probably not that interesting, but for computer science, it's important that you should not check this condition, this growth condition for all j's. You know that you may stop this checking the condition on the level j1, which is comparable with the iterated logarithm of n. This is a simple idea that you cross some level, then it's pointless to continue the procedure. But obviously, it requires some lines of the proof. Okay, and so the most important idea to have the algorithm working in the polynomial times in the number of elements in the set T is to replace the functionals. The functionals unfortunately require subsets of the set T, and there is plenty of subsets of the set T. So we want to replace them by simply functions on the set T, and the functions should satisfy two conditions. First one, that they are decreasing, and this is our condition 2, and the second one is that they satisfy sort of idea of the Sudakov minoration. And the idea is that if we have any family of points in a ball of radius given a negative j, then if we can find points that are well separated, but on the level lower, so a negative j minus 1, here we put 1/2 because all the idea requires such pay here. So, and then we need that the following growth condition works. So fjt must dominate the following quantity, and then we can show, and I will show it in a second, that the whole idea works. If we consider fja just supreme over this family of functions on the set A, this functional satisfies the growth condition. That's what the idea is based on. Okay? So now, what is our aim? Our aim is to prove that if we have a family of functions that satisfies 2 and 3, we will see that functionals defined in this way satisfy the growth condition. Okay? So to check that the growth condition is okay, we just need to consider a family of sets hi that are contained in balls of small radius around some point pi, and we know that since hi's are some points in the set hi, then they cannot be too far from the point ti, because there is a upper bound for the distance, and that's why if we compute the distance from xk to xl, then we will see that still we can gain something comparable with a to negative j negative minus 1. So points are separated on the level which we require in the formulation of our functions. So the next step is to see that if we assume, that was my basic assumption, that all the sets are in the ball bt r negative j, then if we have the point that on which the supremum is attained, all the construction is for t which is finite. So there exists some point x on which the supremum is attained. Then we know that also this family of sets is contained in the ball around set in the around point x, but we have to pay that the constant is 2. 2 and negative j contains the set, but that was our requirements for the functions, for the function fj, and that's why, due to definition, due to our requirement of the functions fj, we know that the following inequality is satisfied, and this is exactly, if we recall what's the meaning of xi's and x, we have exactly the partitioning, the growth condition for Gaussian for functionals fj. Okay, so now how to construct the function, and this is the basis of the algorithm. I just want to slightly simplify it. This is the core of the idea. So you need, because this is computer science in the sense, so you need to know that everything can be computed in the right time. So you also need to accept of the fact that you need to control the number of points in the set T. You need to probably control also that the points are in some space R2 n to some power d, because you have to compute distances in the right time, and in my view it's possible only under such condition if we work with canonical processes. Okay, so we recall that we should somehow understood what is the diameter of a set T, because it's also important when bounding Gaussian processes. And now we start the construction, and this construction is simple. If we cross the level J1, as I've said, it doesn't matter what we choose. So we choose just simply 0 because it's unimportant. The important part starts when we are in the right regime, so we are between J0 and J1. Describe when the picture is of interest. And then the idea is to construct some separated net, and now we need, it was half r negative j minus 1 separated net, and now we have 1 over 4 n negative j minus 1 separated net. So once and once it must be a little bit smaller. And here, that's the most important part. So if we are using greedy algorithm here. So we're just looking for so as a first point, xi point where there is a maximum over functions fj plus 2. We know what they are because we know from where the construction starts. We know that there is 0 if we cross J1, and then we are finding the next best possible points, and we are doing it this way. Each time we are just removing all the balls around xi's that are of radius 1 over 4. In this way, we construct a net which is 1 over 4 and negative j minus 1 separated. Okay, so with each point t, we can match some point which is close enough to point t. If it's 1 for separated, we can always find such point x, and we want to use the one which is the first in the order. So the first one which appear is of interest for our purposes. Okay, and why this idea should work? Because now we can define our function fjt in the following way. We can check all the possible points that are in the ball around point t, and once again a little bit larger diameter. It shouldn't be -1 here. 3 times n negative j, not j minus 1. It's my mistake. And we should check all of them here. We can put them in the right order, so we need this right reordering. And then we define fjt as the maximum over all possible m that are smaller than p, and we take what should be for Sudakov minoration, and each time the fj plus 2 with the point xlm, which is another in the order I've mentioned. And always we have to take maximum of these quantities with fj plus 1 t, because we need to satisfy also the second condition I've mentioned, that these functionals are decreasing in some way. Okay, and now I would like to convince you that this is the right algorithm for finding this gamma 2 approximation, and the reason is that the condition 2, as I've said, is for free because it's in our definition. So it's not there is no problem with condition 2. The problem is to establish condition 3. So there is a problem with a growth condition for the family of functions. And what we have to choose when proving this growth condition, we have to check any possible family of points that are contained in the ball T to R negative J, that are separated on the level half and this quantity. Once again, we can reorder them because it's for free. We can reorder points that we have to deal with, and what we know by the construction, we know that for each point ti there is its approximation in the set X, and the approximation is not farther than 1/4 n negative j minus 1, because it is due to our construction. There was projections on the net I've provided here. Okay, so the core of the algorithm is that we have the following inequalities. So if we consider fj plus 2 on the point tk, it has to be proved that it's always smaller than fj plus 2 on the point xlk. Yes? And I recall that all these points are ordered in the decreasing way. So we're starting from the first one. We have to use the induction here. So we have to start from the first point, and first point T1 obviously must belong to the ball of this radius. So it's always smaller than all possible points in this set. But on the other hand, since on the right-hand side we have the first point that enters the ball of the radius 3 R negative j, it is obvious that we have this inequality, because each ball that was removed before this xl minus 1 doesn't cross the ball bt to R negative j. And that's why we have this first step of the induction. And then it's obvious what have to be done. We just use the idea to prove the induction step. So we are starting, and if we want to upper bound fj plus 2 on the point tk plus 1, it is clear that we have to look over all possible sets, but we've removed points that were used before. And because the net is, because points ti are half n negative j minus 1 separated. Okay, so we can remove all these balls, but if we removed them, it's even worse if we removed smaller balls, but around the points that are in our 1/4 n negative j minus 1 separated nets. So if we removed them, but the worst possible case here is if we remove them in the right order. So if we remove balls of this radius, but around in the right order xli's, okay? Because otherwise we just missed one of them, and if we miss one of them, we just put here this as the upper bound of this, and that's why it would be even. So I mean that we should that the worst possible case is that if we have them in the right order, and then what is clear is that in this way we can prove defining fjt as the maximum over the quantity from the Sudakov minoration and the minimum over this stuff, we know that this is they can be lower bounded by fj plus 2 ti's, and this is exactly our requirement for free. And that's why the growth condition is satisfied, and we know that this algorithm works for finding lower bound. So now, why the algorithm is exact? So why it gives us the right approximation of gamma to numbers? So the reason is the simplest answers, the simplest proof of the fact is that we can prove that fjt are always dominated by some up to some constant supreme over the ball with, once again, a little bit larger diameter for R negative j. Okay? So the reason, the idea is to once again use induction. We have two cases. So it's unimportant when we cross the level j1. So when we've put the functional to be equal 0, if we are in the right regime, so if we know that our definition is of meaning, so we have to consider two cases. The first one, if we know that this is exactly j plus 1t, but then it's pretty simple. If we have this inequality, we also have the inequality with a larger diameter. And in the second case, when we have to use the definition, so we have to consider points ordered from our well-separated net in the ball of diameter 3 and R negative j. So we know first that they are located in some ball of right radius. We know that are well separated. And we can use simply by induction bounds for j plus 2. So we can provide here these quantities. And we are exactly in the partitioning scheme for the Gaussian processes. So we can use the simple Gaussian partition scheme, which says that it can be dominated. If we choose the constant k here, it can be dominated by this quantity. And in this way, we prove that our algorithm is exact because finally, we have that the supreme over fj0 is by ft, and ft is the expectation of the supreme over Gaussian process, and the expectation of the Gaussian supreme due to the Talagrand's theorem is dominated by gamma to numbers. So in this way, we've constructed an algorithm, and if you look carefully how it works, you will see that it works, I think, if the computation of distances is for free, I think it's in the n squared operations unit. At least I think it's comparable with this quantity. Okay, so now we would like to move from this nice picture to the case of canonical processes. And for canonical processes, unfortunately, the difficulty is that we don't have right that there is no right one distance to control all the process. We have to use family of distances. As I've mentioned, you can think of this family of distances. We can think of them as the 2 to the power n moments of increments. And the most important, it was mentioned once again. It was part of the talk of Tomek Tkocz, that we need some regularity here, and the upper bound here is clear because it's satisfied for log concave in the canonical processes, but the lower bound is not that obvious, and it doesn't work for Bernoullis. We need that there exists a small epsilon greater than 0, so that dn is dominated by dn plus 1. So the moment 2 to the power n is not exactly equal the moment to the power n plus 1. Okay, that's very important here. And then we can define what is a ball for each such distance, and what is important due to this funny inequalities for distances is that we have some inclusions for balls here. And you will see that if you are in the case which is important for what I mean to say in a moment, so we consider ball in the distance n and of radius 2 to the n and r, negative j negative 2, the last one is okay. Then we have the following inequalities. So if we are increasing n's, so they are larger and larger, we have the very nice relations between how the balls lies in relations to. Okay, but the more important thing is that they are not too large, and for the fact that they are not too large, the important thing is our requirement that there is some epsilon we can use here. We can use two things. That here we've got small epsilon, and here we've got kappa, which can be relatively large as we want. So if we look here, we will see that by our relations we can always say that this ball is contained by the ball in the distance n. So this is the hypercontractivity. So we are using much worse, in a sense, distance here, but still what we can gain here, obviously we're losing the constant because here is kappa, but we have here j minus 2, and we know that r is of this type, so we can just remove 2 and replace it by 1 with this consequence. But also we have j plus epsilon to the power kappa, and this can be pretty large, and we have to this quantity to be as large as we want. This is the core of the proof of a lower bound in the general case of canonical processes. Okay, so now we move towards families of functionals. So the perfect picture of Gaussians was that we could use, in fact, one functional. Here we can describe all the situation with functionals that are double indexed, so indexed by n and j. We also need them to be decreasing in this sense. We need that they are increasing as the functionals on set. So if A is in B, then the functional increases. And the growth condition, which I can now describe in the language of distances I've introduced, is that if we have points here in the ball of radius 2 to the power n negative j, in our distance dn, then if the points are well separated, so each increment is greater than what's given here, then if also I can control sets hi, so each set hi is contained in the ball. Now I'm moving the distance, I'm using the hypercontractivity, moving the distance to n plus kappa, but also the only point which can help me to make this set small, and this is obviously important because it must be similar to the Gaussian case, is that I'm using here r to negative j minus 2, okay? And then whenever this condition is satisfied, we say that satisfied is growth condition. The consequence will be that something similar to Gaussian case can be stated. But what I've meant is that our requirement of this regularity between distances provides us that here we have that hi is in effect small comparing with what we are starting. Okay, and it must be satisfied if we dream about a result comparable to what we know for Gaussian. Okay, this is a general partitioning scheme, and unfortunately, the most important difference is that we need here, if we now replace the functionals by functions, which was the idea of an algorithm for the Gaussian case. Unfortunately, it has to use this function have to use this double index, and the fact that these functions were decreasing in J was pretty clear, but they are increasing in N. Obviously, when constructing such function, we can demand this condition, but it would be very hard, and that's the real challenge for finding this algorithm for canonical processes. It will be a real challenge to prove that we have some upper bound which is decreasing in N, okay? Because it's not natural for the construction. So why such a growth condition is of importance? Because whenever we have a growth condition satisfied, there is a proof which Jelani told us in the morning in the special case of Gaussian partition scheme. The lower bound, which is based on construction some partition, and the partition is admissible, the first one. With each set in such an admissible partition, we can construct also numbers that are some integers in Z, and we know that behaves in the right way, so they do not increase too fast. And finally, the most important part is that we can control the functional NA0 J0 by from below by the quantity that is the core of any lower bound idea. So this is the chaining. So this is a gamma 2 quantity which we want to upper bound by our family of functionals. And so in particular, if we are in our case of canonical processes, so I will say something about this in a second. Then we will learn that this is upper bounded by something like that whenever the growth condition is proved. So the point is to show that I can have this right condition. Okay. Once again, it's important, but fortunately, this idea works for computer science. It would be important that you don't need to check all the growth condition for all J and N. You just need to concentrate on N in special regime, and also J is controlled by similar stuff. So there is no problem with the fact that the family of the functionals to check is too large. No, it's not a problem. And maybe just one comment. The core of the idea, it was because Jelani showed us the idea based on some trees, but in fact the core of the idea is to check that the growth condition works like that. We have some partition element, and in effect we have some, say, n-1 step of the partitioning construction. With n-1, we have prescribed, for example, some j-1. Then, if the j-1 is not replaced by j, we know that we have a possibility, so in the next time step, we know that there is a possibility that we can gain, because it's exactly stated by the growth condition, that we can earn something. And if we can earn something only if the diameter of our sets will shrink sufficiently fast. So the next step, which is important, is that this number increases. It means that the first time the diameter was shrunk first time, and then we have n plus kappa next steps in which we were waiting. If there is a chance that once again we can we can increase the number j. So once again, the diameter was shrunk. And if this occurs in any p where p is smaller than kappa, then this pattern in our partition scheme is the only one of importance. So we are proving, and this is a very tricky idea of Talleyrand by using some strange order, but only such patterns are of matter. And you can see that the partition scheme exactly refers to the fact that on each such pattern, we are again what the Sudakov-Mine ration offers. And if you understand the idea, you will see that necessarily we've got the most important part, which is we gain by partition scheme the right quantity, which is stated here. So this is the same. This is the core of the idea that Jalini was going through for Gaussian, but it works in the really high generality. It's the most general as I know, as using partition scheme in the context of canonical processes. Okay, so now what I should say now is why the growth condition is satisfied for canonical processes. And the first part is the Sudakov-Mine ration. And we have Sudakov-Mine ration because Tomek told us everything about the fact. In the case of independent data, I will say something about Sudakov-Mine ration because it's something that interests me much. In the case of dependent data, but here we know that, for example, because it's obviously important that for log concave isotropic vectors or just variance 0 and symmetric, we have the Sudakov-Mine ration, and we can state it exactly in the order we need this fact. So if the points are well separated in the distance, say, n+1, but also by our hypercontractivity in the distance dn, they are well separated, we can demand that the expectation over such supremum is of right order if we multiplied it by some constant, say k here. So the next point which we need, and also it was mentioned by Jelani in the morning, the next point which we need, we have some concentration inequality, but it's important here that we need the concentration exactly around the mean of supremum of such a process. So we need that say, there is a concentration around the strong moment, so the expectation of the supremum by weak moments if we consider p moments of such differences. And I think that one more thing to establish the growth condition, I recall it one more time, is our comparability, because you will see in a second that it's absolutely important that we have at least something that dn plus 1 is dominated. So at least there is at least 1 plus epsilon, which we can put before dn. This is inequality. Okay, so now the idea, and the idea was mentioned in the morning. If we have a family of distances, so if we have family of distances, we can always split this. So we can choose the one of the random variables with pi as the point in hi, or just in the ball that hi is contained because it suffices here. Then we will have some remainings, and then we just need the expectation of the remainings, but now with the minimum over this family. And what left is something which have to control from above, because it's something which we have. which has to be compensated by our gain from the Sudakov minoration. And as you can see, this is the right quantity, and we like it, and there is something which left. And now, if we have supremum over a given family of points, the same idea as Tomek-Koch told us will lead us to the fact that if there's many of these sets, and many means controlled by 2 to the power n, then we can replace this quantity by the supremum over all possibilities. But here I have to put 2 to the power n moments. So the inequality is of this type, and with some constant here. And the constant in our case is, I think, 2. But you could put here anything, and the only idea would work. So it doesn't matter. But I think 2 is the loss you've got when going from this to the 2 power n moment. And the final point is that this is, if you look at this is exactly the diameter by our concentration inequality. This is controlled by diameter, or in the diameter in the dn distance of the set hi. So what is the conclusion? The conclusion is, now, if we can control the diameter of a set hi, then we are done. And the idea is, once again, I've mentioned. So we can control dn hi because we can control dn plus kappa. That was the main requirement in the formulation of a growth condition. So we can control this quantity. But we know that when we are going from n to n plus kappa, our gain will be that I can divide this diameter by something that can be reasonably large. Even if there is a very small epsilon, I can compensate it by taking kappa, which is that large, that it can kill any constant I need to kill to establish the growth condition. And here, finally, we've got our inequality, and that was what I've mentioned, that dn plus kappa is exactly bounded by the quantity. And since 1 plus epsilon to the kappa can be any large I want, I can kill this constant, so I can replace it by 1, and then I will gain exactly 2 to the power n r negative j minus 1, and this establishes the growth condition for canonical processes, okay? So this is the whole idea which works for canonical. And my small comment about dependent case. Dependent case is difficult because we need the Sudakov minoration, and the minoration is a challenge. We do believe that the Sudakov minoration works when, in the following setting, when there is a isotropic vector, isotropic log concave vector, which satisfies the one unconditionality condition, one unconditional, which means the distribution is of this type. And everything here is, so the random signs are independent of modulus of variables zi. Okay, so this gives the picture symmetry and allows to use Sudakov minoration for Bernoulli random variables. It's important to establish the result. And but even in this setting, my belief is that two-level concentration, which is the concentration satisfied for exponential measures, is the right condition under which the Sudakov minoration could be proved. Up to now, and in fact, it's also quite a challenge that any move from the independent case is possible. And what I can state is that under some weak independence condition, something can be done. And obviously now, by the idea I've dwelled on, which is the comparability of distances. So if you assume all this stuff, we can say something about dependent data. Okay. So the last two slides I would like to show concerns the question. Okay, so maybe the question about computing the expectation of a supremum, or at least quantity comparable to it, maybe the question can be replaced by some comparison. So we don't have to check what is the estimate for BT, but we can compare it with something which we already computed. And this can be formulated in this way. Suppose we have a mapping, and when we have a mapping from the set T, which was in L2, to some nuance subset of L2 space. And the question is, can we compare expectation of supremum for these two sets? Okay. So what is well known here is that there is a Bernoulli comparison theorem, and the Bernoulli comparison theorem states that if we can compare two processes if the function is a contraction on each coordinate, and this is exactly meaning what's the contraction on each coordinate, and the contraction on each coordinate allows to say that there is a comparability, and the comparability is with constant 1. Okay, so is it possible to say something more? And the conjecture. And the conjecture here is as follows. Suppose we can prove that increments are dominated, so each moment of increment for one set is dominated by p moment of increment in the second set, okay? Suppose we can show this inequality. Does it improve or not that there is also comparison of expectations? And so obviously, you can see that, once again, from the view of computer science, to check these conditions, even for all points in the set T, is much less difficult than finding an algorithm to find BFT. So that's why it may be of interest. Okay, so the second, so I've stated the Bernoulli comparison theorem, but also it's pretty clear then if BT happens to be comparable with gamma x, or in general with my bar gamma x, then the result is obvious, because by the construction of gamma of x, we know that the whole idea works. But what I can prove up to now is that is something like that. If you can compare Gaussian parts, and Gaussian parts stems from the understanding what is the norm of Bernoulli canonical process, and we know that p moment of Bernoulli canonical process is the following quantity. So you have to reorder coefficients so the reordering is non-increasing, and then you have to select first p of them, so the p greatest one, and then the left is of Gaussian type, and it should be multiplied by square of p, as in the Radek stock. We know that this is something usual for p moment of Gaussian random variables. And this part, I would call this part the Gaussian part of xt p moment. Okay. So now, if you can compare these parts of p moment for the set T and set phi of T, then the result holds. So in general, it can be stated like this. So if we can compare in this way moments, you end up with comparison of expectations. And the proof goes through some ideas from our proof of the Bernoulli conjecture, but it's not that difficult. One simple conclusion of it, to see that it's pretty stronger than the Bernoulli comparison, is that if it means something like that. If you remove p elements from our understanding of p moments, so just takes distance, but we've removed constant times p coordinates. Okay, and if you can prove with some constant which can be any large, you want that it's dominated by something similar for the set T. We've removed first P elements, then we know that there is a comparison. Okay, and the result of this type would answer the Oleszkiewicz question, on which I end my talk. So the Oleszkiewicz question is whether the strong moments of vectors with random signs in any Banach space, to verify the condition, does it or not suffice to check that weak moments are comparable. And that's all what I meant to talk to say. Thank you.
Two questions. The first question is, in your first slide, you stated the Bernoulli theorem.
Okay.
Is there an efficient algorithm to construct T1 and T2?
So the problem with our construction is that it goes from up to down. And obviously, you could say, if I can compute each expectation supremum, our algorithm gives you right construction, how to construct this decomposition, because this is essential, the core of the proof. But as I've learned from the Gaussian case, what you need is to go from down to the top. And then it becomes difficult due to what I've said, even for canonical processes. The construction is difficult because if you define this function f and j, and something similar could be done for the Bernoulli case, then the difficult part will be to somehow well upper bound this function f and j with something that which is decreasing in n. And I can tell you later. This is the core for me. This is the main difficulty. If you want to something that is reasonably fast. So if you need to compute some estimate in the polynomial time in the cardinality of set T. So our algorithm is obviously the construction. So you have the construction, but still you have a problem how to compute if you go downward. If you have a difficulty computing the decomposition because you don't have the expectation of supremum over decomposition. So that's the challenge.
One more question.
Okay.
So I guess the last slide, or the second to last slide, we had that corollary. You said if there exists a fee, then you get a lower bound.
Yes.
I mean, were you hoping that one day someone will, there will be an efficient algorithm
So
to construct this fee?
In my opinion, one should find contradiction to my conjecture than the comparability of moments. But for me, it's really difficult because if you start to think of it, nothing easy would work. So if there is a counterexample, so comparing two moments of two families, surfaces, it must be complicated. This should somehow look like tree and some complicated tree. And I think it's also quite a challenge. But maybe if the picture is like that, then it would suggest that there is some better understanding of the Bernoulli conjecture. So maybe there is a better formulation, as I mentioned at the beginning. There is some better formulation of this gamma x functional. It would be not the one I've stated, but maybe some better formulation which would work. But I don't know.
Let's see.